the summer Milky Way, you can see Aquila, the eagle, winging its way northward along the river of the galaxy. Off the western wing, shining brightly in light your eye cannot see, is the Hulse-Taylor binary pulsar. 21,000 light-years from Earth, the system is comprised of two neutron stars, the tiny skeletons of dead stars orbiting one another. Spinning almost 20 times per second, one of the stars is a pulsar, directing a powerful beam of radio light toward the Earth, a built-in clock that allows us to watch the system evolve over time. General relativity predicts that when two compact stars orbit very close to one another, they will emit gravitational radiation, carrying away energy and driving the stars together. For 40 years, astronomers have watched this system and noticed its orbit shrinking by about 3.5 meters every year, at exactly the rate predicted by general relativity. Can we see these waves directly? The first person to seriously contemplate this was Joseph Weber at the University of Maryland in the 1960s. He used a 1.5-ton cylinder of aluminum suspended on a wire around its midpoint. If a gravitational wave passed through the bar, it would stretch it. The forces between the aluminum atoms would pull it back to its original shape, and it would faintly ring as if you tapped it with a tiny hammer.
Hello, welcome to Roundtable. I'm your host, Lee Artz from the Department of Communication, and I'm joined by my guest today, Shane Larson. He's an astronomer at the Adler Planetarium. His expertise is so wide and impressive, I want to make sure I get some of these things right, because you're also an associate professor in physics at Northwestern, and you work at the Center for Interdisciplinary Exploration and Research in Astrophysics, which is housed at Northwestern.
Yes.
And the things we're going to talk about today will be, we're going to play Mr. Science a little bit maybe, because Dr. Larson works in gravitational wave astrophysics, which is a mouthful, and I'm sure everybody understands what that is already, but I would like to
by the time we're done.
Right.
Yeah.
I would like to start with just, I mean, when I think of gravitational waves, I think on an ocean and the wave comes in and I roll and I can feel it, but what exactly is a gravitational wave?
Well, so let me start a little bit earlier than that,
good,
right?
okay.
So you know, when you take an astronomy class or you watch the news or you open up a magazine, what you normally see are pictures, you know, taken by telescopes and the Hubble Space Telescope and NASA and all of these sorts of things. So almost everything you know about astronomy, we've learned by using light of one form or another. And the whole idea of gravitational wave astronomy, which is what I work in, is that there are other ways to discover things about the cosmos than just using light. Light is, in some sense, a natural way to try and discover the world.
That's how we see things.
That's how we're used to that. Sight kind of dominates our senses in many ways. But Einstein, roughly 100 years ago, had this notion that there were other ways to do this, that you could in some way sense the gravity from distant astrophysical objects and use that to tell you something about where they are and what they're doing.
Right there,
so.
I need to know what's gravity then. That's a force.
Okay, yeah.
That's a force that attracts to each other?
Yeah,
or
so
is
that's
that
the way
more...
we've traditionally learned about it, right? So gravity is one of those interesting things that you encounter in your everyday life. It's kind of always there, and you don't really think about it unless you're told to think about it, right? It's kind of remarkable that we actually figured it out. You know, you walk around and you fall downstairs and you drop your coffee cup, and if you never stop and ask, well, why did my coffee cup fall on the table, or you know, why am I stuck to my chair, you might never have stumbled on this idea that there's something in nature that makes those things happen. And in the kind of middle of the last millennium, the 1500s and 1600s, people really started to ask that question. Why do I stick to the ground? And why does this rock fall to the ground? And the first kind of experiments were done early on by Galileo. and various other earlier Greek scientists as well. The first kind of extrapolation to astronomy was done by an astronomer named Johannes Kepler. And then the formal kind of mathematical physical definition that we use today to fly satellites and send astronauts to the moon was worked out by Isaac Newton. And so
I understand Kepler's is planetary motion, and is
Yeah.
that based upon gravity, that things will move? Or
So this is one of the remarkable stories about physics, right? Is Kepler was trying to understand what then was a new idea, which is the planets go around
Yes.
the sun, right? So that was the kind of notion that Copernicus put forward. And Kepler was trying to understand, well, why is it? Why does it happen that way? And he derived these things that we now call Kepler's laws. They're more traditionally called the laws of planetary motion, as you said, but they describe anything in orbit. So stars around the galaxy, planets around the sun.
his laws, are they based on gravity, though? I'm coming back to this question
so
of gravity.
The way Kepler derived them,
Okay.
they were based on observations only. They're what we call empirical laws, right? You look at the universe, you see what's going on, and then you say, oh, well, I don't know why that's happening, but here's a rule that describes what's happening. So Kepler did that in the, 1600s. And it wasn't until 100 years later that Newton wrote down what we call the universal law of gravitation,
Okay.
a mathematical way of describing gravity.
Describing what Kepler saw.
That he could
Okay.
describe why Kepler saw what Kepler saw. So it's one of these kind of stunning, progressions in physics where we had kind of known for a long time what was going on. We made an attempt that didn't quite get all the way to understanding it, and then later on, someone finally figured out what it was all about.
Okay, again, I'm still kind of stuck on the word gravity. So
Mm-hmm.
the Kepler defines how these planets move. Einstein says this is because of gravity, but
No, Newton
I'm
said
sorry,
that.
Newton
Yeah,
says
that's
that it's
right.
because of gravity. But what is the gravity? Is it an attraction? Is that why? Because it would seem like if it's the attraction, if you're farther away, you would just kind of be released.
So this is the heart of what Newton decided. Newton decided that every object in the universe attracts every other object towards it as virtue of this quantity that we call mass. How much stuff are you made of? And his representation of gravity told us two things. It said that the more stuff you have, the stronger you pull on everything. And then what you said, the farther away you are, the weaker you pull. So right now, you and I are experiencing a very strong gravitational force between us because we're sitting next to each other. But if we were to scoot back 10 feet, that force would be weaker.
So why does the planet, I mean, this may be off topic, but
No, that's perfect. Yeah,
I'm
that's a
curious
great question,
here.
yeah.
Why does the planet come back then? Because if the force gets less, you would think it would be, I've escaped. It's like teenager leaving home.
So what Kepler discovered was the sun was the source of gravity in the solar system. So imagine my coffee cup's the sun, and this cube, which is not like a planet, but let's pretend it's a planet, okay? The planet is traveling on a straight line. So if this is a planet, it is flying through the universe, and the first law says it's going to travel in a straight line and never change. Okay, now let's introduce this thing we're trying to understand called gravity, right? So this is what Kepler discovered. He said, well, the sun's here, and the sun appears to be pulling on the planet somehow. So what does that mean? It means the planet wants to go this way, but the sun's tugging it that way. So it starts to travel this way. Well, now it wants to go in a straight line, because that's what the first law tells me, but the sun's pulling it, so it starts going this way. And so it kind of goes around and around in this circle, because the sun's always pulling it away from that straight line motion that it wants to go in. And so there are neat demos we can do. You can go home and tie a tennis ball on a string, okay? And if you whirl it around your head, the string is like the force of the sun pulling the tennis ball, which is like a planet, in a circular orbit. But if you let go of the string, that's like the sun vanishing. What's the tennis ball do? It flies off in a straight line and breaks your living room window, right?
Okay.
So, yeah.
I still don't understand why, when it's at its farthest point, it gets pulled back towards the sun. Because if we're closer to the sun, there's more gravitational pull.
Yep.
The farther away we are, the less gravitational pull. So the tendency would be for it to leave as opposed to come back.
So let's do a slightly different thought experiment. We could do all these experiments for real if we wanted to, but we're here in the studio, right? So let's suppose I wanted to throw this object into outer space.
Yes.
Okay? So if I just kind of throw it up in the air, it only goes maybe 6 inches, and then gravity takes over,
Yes.
and it pulls it back to my hand. Okay? What if I want it to go higher? What do I do?
Oh, it's still going to be pulled back no matter how far away it goes.
That's
it
right.
just takes longer for it to come back.
It takes longer to come back.
Okay.
But if I throw it hard enough, if I throw it fast
Yes.
enough,
Or if you
then
have
I can get away.
If I have a propulsion to get it away
That's
from me
right.
because there's
Yeah.
another force.
So we call
leading-
that escape speed. And you're absolutely right. If I'm farther from the sun, it's easier to get away from
escape,
the sun because
right.
the gravity's weaker.
Okay.
Yeah.
Okay, I've got the concept of gravity now, and then the question is, we see it like Kepler saw it, and Newton provides the theory, but you're measuring gravitation
Yeah.
that you cannot see, so there's no witness of it. So how can you do, this is in waves, but how do you know that there are waves? I
Yeah.
mean, what's the measurement of that?
So so there's kind of 2 parts to that we have to talk about. So one is, how is this different than what you and I were just talking about, forces? And that was something that Einstein stewed about for a long, long time, because he was the one who taught us that nothing in the universe can travel faster than the speed of light. And when he discovered that, physicists very rapidly came to the conclusion he was right. They could go to the laboratory and prove it, and it's been proven 1 billion times since. He asked the following question. He said, well, what happens to gravity? If I move the sun, the gravity that the planet feels has to change because, as we just discussed, the sun's farther away. Well, that information can't get to the planet instantaneously. It has to take some time. And so Einstein's whole idea of how gravity works was centered on trying to understand how to make gravity behave, or how to describe gravity
how it
in
does
such a
behave,
way that it doesn't propagate faster than the speed of light. And the ultimate conclusion that he came to is that we live in a universe that has these propagating disturbances in gravity that we call today gravitational waves, that are the consequence of the fact that nothing can travel faster than the speed of light.
Maybe very quickly you can tell me how do you know the wave is there? Is that going to be something that we should have more time for?
So physicists argued about this for 50 years, and Einstein proposed this in 1916, and it wasn't until 1957 that we figured out how to answer that question. And it was that idea in 1957 about how do you measure the waves that led to the gravitational wave experiments we have today, LIGO, LISA, other gravitational wave experiments.
LIGO?
Yeah.
Which is the Laser Interferometer Gravitational Wave Observatory. And you said that there's actually 2 of them.
There's 2 of them.
Why would you need 2?
So there's 2 of them for 2 reasons. One is that these devices, these instruments, act in concert to detect these gravitational waves. And the way they sense the universe acts more like your ears than it does than your eyes. Your ears can sense signals, sounds from anywhere around you, whereas your eyes can only look in a certain direction.
So are they listening? Is
So
there some other
we don't have the right word to use for them, right? Because this is sensing something about the universe that your body isn't designed to do. And so sometimes we say see, sometimes we say listen, but really what we should say is observe or detect, because this is something that's completely new and completely different compared to what our bodies are used to.
So these instruments measure or observe or detect, but are these like radio waves? Are they gamma rays? Are they
so these are
pressure? I mean,
so everything in physics is a wave, right?
Okay.
And these are many waves you've listed, but these are gravitational waves. And so what these are is these are propagating disturbances in the structure of gravity itself.
And they can measure this.
And we can measure this, okay? And Einstein thought this would be an impossible measurement to do, okay? But you and I live in the future, and we can do it. And we built the instrument like LIGO, and we're going to build other instruments like LISA, which I also work on to do it. So what are we looking for is really the question, right? So the way Einstein describes gravity is slightly different than the way we started talking about in terms of force attracting each other. Einstein, through what we call general relativity, said there's this other way to think about gravity that in the instances that we're used to is completely equivalent to forces. But really you can think about gravity as being how the shape of the fabric of the universe is put together. we think of gravity as a warpage or a bending of the shape of space and time. And so what LIGO is measuring, what LISA will measure, is how does the changing gravity that's propagating through this area in the universe change the shape of space and time inside the LIGO instrument.
Is that because all of the objects inside the universe have different gravitational pulls, and they're acting?
Well,
are they acting against each other or with each other?
They
so
can
it's like
and they do, right?
A ripple comes through, and it,
any heavy object changes the shape of space and time around it. Okay, now this object in my hand is really light, so it's not changing space and time very much. The Earth is quite a bit bigger, and the sun's even bigger still, and black holes and neutron stars are even more.
Like a large person walks into the room, you kind of
like,
you feel the presence.
Ping pong balls versus you on a trampoline, right? You bend it a lot, the ping pong ball doesn't. So the gravitational wave changes that shape of space and time. So I typically show this as a bungee cord that I show people, right? So imagine, so LIGO is basically this big L shape. It's it's a laser interferometer.
Each one is, or between
each one is a big L, okay? So from the corner all the way out to the ends is 2.5 miles, 4 kilometers. Okay, so you can think of this bungee cord as being one of those sides of the L. And when the gravitational wave goes through LIGO, what it does is it stretches that LIGO arm. Okay, now you may not be able to see it, but there's some marks on that bungee cord, right? So you can imagine those are like tick marks on the ruler. So if I just put tick marks along the arms of LIGO, and then when it's stretched, if I just count tick marks, I can't tell it's stretched. So how do I tell that the space-time was stretched? Well, the way you can measure it is imagine an ant walking along my bungee cord. Okay? The ant may take, say, a minute to go from one end of the bungee cord to the other. But if I stretch it, it takes him longer to go. So this is what LIGO does. We have a laser beam that we're shining up and down both of the arms. It flies down the arm, and it hits a big mirror that weighs about 40 kilograms. And then it comes back, and I time how long that takes. And when the gravitational wave comes by, if it stretches the LIGO arm, the laser beam takes longer to get back to me. And if the gravitational wave compresses the LIGO arm, the laser beam gets back sooner.
One of the remarkable things for me that's kind of outside the science is that the LIGO was there for years and didn't discover anything. They're stretching the beam, and how long was it? 10 years, 20 years?
So the very first, what we call initial LIGO ran for about 8 years, as I recall.
And didn't find anything.
And we didn't find anything because we knew this was hard, and we didn't expect to the very first time we tried, right?
The thing that strikes me is in a world where the federal budget, for instance, has to be given only for those things that somehow can show progress. That you continue to receive funding for LIGO. I mean, it's even more complex than climate change. But to believe that.
So in 2011, we tore initial LIGO apart. We put improved lasers in it, better mirrors, right? And now it's what we call advanced LIGO. And in September of 2015, we turned it on, and we detected, 2 black holes almost right away. But that's because we improved the ability. It's the same way, it was just a little bit better than it was before. And
so when news reports said they heard something, it's the same as saying
detect or observe,
the gravity,
or we saw.
There wasn't actually a sound that took place.
No, this is why we have 2 detectors, right? The LIGOs were sitting there doing their thing, and when these black holes go off, they stretch and compress the arms of LIGO with a certain pattern. And we saw the same thing happen in Louisiana as we saw happen in Hanford.
One reinforces the conclusion of the other.
And the fact that you saw it in both of them is what convinces us that we saw something.
Excellent.
Okay. So why? Why do we need the 2? That was why you asked, right? Okay, because the LIGO arm stretches by a minuscule amount, and such a tiny amount that if I didn't see both of them stretch in the exact same way at the same time, then I wouldn't believe it. Okay, so you should ask, right? Well, how much did it stretch by, right? Okay, so the LIGO arm is 2.5 miles long, and it stretched by a small amount that is equal to 1/1000th the diameter of a proton.
And they both did.
And they both did it at the same time, up and down,
And how do they know this wasn't a shifting of the Earth?
Well, that's a good question, right? So because it hit in Louisiana first, and 7 milliseconds later, it hit at Hanford. So that's how long it took something traveling at the speed of light to go from Hanford
what
to
you're saying is the gravitational wave was there. So
it went by, and then the shape of how we plot the stretching of the arms was exactly the same. So we know it wasn't, a truck driving by or a student bouncing the basketball in the hallway, right? Is because it would be different in both places because you're not synchronized the way the gravitational wave signal would be.
So the source of that wave, can you identify that? Did you say it was a black hole, or?
So the very first event, we call it GW 150914.
I wrote that down. 150914.
So GW
Everybody should write that down.
wave.
GW 1509.
2015. The 1509 was September.
Okay.
14 is September 14.
And then GW is gravitational wave.
GW is gravitational wave. So that's how you read those phone numbers. So it was about, it must have been about 4 in the morning here in Chicago, or here in Indiana.
Did they wake you up?
Yeah. Well, so some people they did, right? But it was a Monday morning, and so the detectors went off, and the detectors are always paying attention. And so the Livingston detector logged an event, and the very first thing it does is it goes and it asks the Hanford detector, did you see something too? And Hanford's like, oh yeah, I saw something too. And they're like, well, we better tell the humans. Okay, and so then it posts it to a log, and about an hour after the event, one of our postdocs in Germany saw the event. And it was 2 black holes, each about 30 times the mass of the sun. Okay, so that's 30 times more stuff than everything in the solar system, shrunk down to a size so small it would fit in the southern end of Lake Michigan. Okay, so these 2 black holes were going around each other. They went around each other about 10 times.
And a black hole is just the concentration of gravity. Is that correct?
It's an object whose gravity is so strong.
Nothing can escape.
Nothing can escape because you can't go faster than the speed of light, which is where we started this conversation, right? Okay. So they went around each other. They collided at half the speed of light. And then they made a new black hole that would, if you put it down on the state, would stretch from one border to the other.
And the new black hole is what gave that gravitational wave, because it was
It's the merger that makes the gravitational wave.
Okay.
Yeah.
Okay.
Yeah. And so this is awesome, because a black hole is an object that doesn't emit light. So if we've learned everything about the universe with a telescope, we can't see them with telescopes.
You can no longer say seeing is believing in this case.
But if we can detect their gravity, then we can actually measure them for the first time directly, and measure their properties and tell you things about them that we couldn't say before.
I have an urgent question that I ask in all of my classes, and it's kind of, who cares?
Right. This is a great question.
Who wants to know?
Yeah.
And we have, I don't know, maybe just a few minutes. Maybe you can give us the...
Well, let me give you 2 answers.
Okay.
Right? So earlier in this segment, you asked me, how did we keep this being funded when it took us so long to do it? And that's a great question. But anytime we build something like LIGO, or we build the Hubble Space Telescope, or we send Cassini to Saturn, we spend $500 million or $1 billion on space missions, but it's not like we're strapping $1 billion to a rocket and sending it into outer space, right? That $1 billion is paying for people to weld the rockets and make the rocket fuel and drive the trucks to drive all the parts across the country, right? That money is getting spent right here in our communities. So LIGO, the tubes, the arms, were built by the Chicago Bridge and Iron Works, right? The folks right here in our area built those tubes for us. So that money that we invested comes right back to all the people who work on it. You only ever hear about a scientist who work on it, right? But there's 10,000 people who made these experiments happen. The other answer to that is, well, what did we do with knowledge like this, right? We've just discovered black holes for the first time and measured them directly. And the answer to, is it going to help my golf game or make me a better gadget in my kitchen, right, is for the future to know. We just barely understand what we've detected for the first time. It will take decades, possibly, for us to understand it well enough that when I have a barbecue with my friend who's an engineer, they can decide how to turn that into something to improve our lives and change the way we see the world. So that's all for the future, and it will happen.
It's kind of like when somebody would have asked Kepler, what difference does this make?
Yeah,
absolutely. He couldn't have predicted the GPS for our phone, or the satellites, or the television, and we wouldn't have Big Bang Theory, which is, I hope this episode was more enlightening than some of the conversations on there. One very quick thing to end. I noticed in this that there's a group of volunteers called Einsteins at Home. Are you aware of it? There's 400 and some thousand people that work with, I think, LIGO, or work with the gravitational wave.
LIGO
These are all volunteers.
Multiple what we call citizen science projects associated with it. So Einstein at Home is a program that runs on your computer instead of your screensaver and looks for gravitational wave signals in the data.
So I can do this on my laptop?
Yeah, so you can just, your laptop's sitting over there right now doing nothing while you're talking to me. It can work on Einstein at Home.
It's measuring gravitational waves.
Yeah. So at Adler and Northwestern, we have a new citizen science program called Gravity Spy. And so this is part of our Zooniverse program, where it's actually a direct opportunity for people to help. You basically log on to gravityspy.org on your web browser. It will show you images of the data, and you can help us classify them to look for signals.
Outstanding. That's all the time we have on our program. Thank you, Shane Larson, for joining me. I'm your host, Lee Artz. Have a great day.
Thank you.